Alrighty, good morning, ladies and gentlemen. Thank you for tuning in. Thank you for all your great questions. I was able to get this working, so I'll go through some of the questions that you asked. I'm trying to combine stuff together and really just show you sort of a summary. If you have any other questions, please let me know and I can sort them out. So the first question that I had was, how do we use this Leibniz notation dy over dx? Now, this isn't necessarily a fraction. This is telling us what's called the derivative of y with respect to x. And that's going to be important for much later. I'll give you a hint as to what it refers to, but basically this is just the notation that we use to refer to as a derivative. Now, you'll see several different types. You'll see y prime. This is the same thing as saying dy dx, which is the same thing as saying f prime of x. It just depends on how we write the notation to start. So when you write a question, instead of f of x, you write it, say, like y equals 5x squared minus x. This is a function of y, so you're taking the derivative of y with respect to x. If it's a little bit more general, like we don't have a second variable, like if it's a function, we would write f prime of x because we don't know what that second derivative is. So just keep in mind that all of these are referring to the derivative, which is how we can find the equation for the slope of the tangent line. So the important thing to note is that in this case, while we are using limits, dy dx is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Now, in this case, we don't have f of x, but remember, f of x is just a fancy way of saying, in this case, y. So I'm evaluating y at x plus h, essentially. So when I plug this in, notice how I've actually written it up here. I'm sort of in my head just replacing this right-hand side with this. So, or another way I can think about it is like y x plus h is here, and then just y x is here. So I'm going to replace the y with whatever I see on the right-hand side. So I'm going to write the x plus h here. I'm going to write the just regular y equals over here, and then I work through it the exact same way. Sort of for me in my head, so in Mr. Sproul's head, I sort of convert this to f of x equals 5x squared minus x. And then I solve it exactly the same way. The main thing is that you're just evaluating sort of this idea of like y2 minus y1 over h as the limit of h approaches 0. But keep in mind is y2 would be equal to 5x plus h squared minus x plus h, and then y1 is just our 5x squared minus x. So that's another sort of way of thinking about it. So you're evaluating the slope of the tangent line. No matter what, set up your function the exact same way and it should be a-okay. I find it's easier in my head to just sort of convert it to this f of x function, but when I write it, I'll write it as dy dx. The other thing I'll point out, when you do limits, hang on to this limit symbol all the way through right up until you do a direct substitution. It just basically tells the person reading that you're still taking a limit, and it also prevents you from forgetting about it. Now, a little bit of a spoiler, this is a little bit advanced, but keep in mind when we talk about things in calculus, they don't necessarily have to be something like a 2-variable problem. We can have more than one variable. Like, for example, I can have a function related to x and y, and that's equal to cos x plus sine y. Whoops. So now it's going to give me a value of something that's different and I have multiple dimensions. Or I can write it as z equals cos x plus sine y. So now it's going to change for every value, and I'm going to get something that looks a little bit like this. So to make clear, this is our z direction, this is our y direction here, so kind of going sort of left to right is our y, and then going this way is our x direction. So this is a three-dimensional surface. You can see it kind of makes this sort of wavy plane, but if we look at this, in this case, I would be looking at the change in my z, so I'd actually be taking dz dx, so I'm taking the derivative of z with respect to x. That's going to give me the slope in sort of this direction. So I can look at the instantaneous slope of anything going along this sort of x-axis. If I took the derivative of z with respect to y, I'm looking at anything going in, let me just change the colors here. I'm looking at everything going in sort of this direction. So over here, I could be looking at the slope going up or going down, but I'm looking in that specifically that y direction. So this is sort of a reason why we use this notation, is that when we get to what's called multivariable calculus and we're looking at different variables, then we can look at the slope of just one dimension at a time. For those of you who are in physics, this is the same way as breaking down your vectors into an x and y component. We're basically breaking down the slopes of this three-dimensional surface into our x and y component. But this is second level, or the second year calculus, so this is sort of a teaser. If what I'm saying sounds like an alien language, don't worry about it. It's not going to be really showing up, but I just want to give some context for why we're using this dy dx. Okay, next question. Lots of you, very rightly so, were asking me about calculators. So unfortunately, my TI-83 doesn't work with screen capture. So the example they gave were with the TI-84, which has a slightly different thing. So for us, the main things are you want to press the math button, and then if you scroll around, or if you just press number 8, you'll see that this brings up something called nderiv. And then it'll have an open bracket. So I'll show you a picture of that in a second. When it opens up, you need to put in 3 values. You need to punch in the function, which I'll show you what it looks like. You have to represent which is your independent variable. So if you have dy dx, you are looking at this variable here. What are you differentiating? And then finally, the point is the value that you're differentiating at. So to show you these sort of 3 steps, number 1, on TI-83 calculator, you're going to press this math button right here. It's going to bring up this window right here. You can see it says math in the top corner. I scrolled down a little bit. It only goes up to 7. You're going to look for this number 8. It'll say nderiv. So this is looking for the numerical derivation. I believe they said that. So you click that, and then it'll open up this piece right here, and it'll open up the brackets. So for example, they wanted, so they gave us f of x was equal to x cubed over ln of x, and they wanted f prime at 0.57. So in this case, x is our variable. So what they do here, or what we type in, is nderiv x power 3 divided by, I like to open up brackets just to make sure that I'm including everything. So whoops, I circled the wrong one. So ln of x, so this is all being divided, comma, here's my variable x, comma, 0.57, and then I click equals here, and it gives me the same value that you saw in your video. So I'm going to show you a couple other ones up here. So for question 27 and 28, if you have access to the emulator, you can actually screen grab. So here, cosecant of 5x. We don't have a cosecant button directly, so one of the things that you can change is that if you remember that cosecant of x is equal to 1 over sine x. So in this case, cosecant of 5x is going to be 1 over sine 5x. So I've already done my math. Click to 8 and derive 1 divided by open bracket sine of 5x close bracket comma. So this is my f of x. Here is my variable x. You're almost always going to be putting x unless, for example, if it gave you, say you had question 32 and it was f of t is equal to 8t squared plus 2t minus 3, then this would become a t. So you would write this in with t, and then, so you'd have n deriv, comma, 8t. And then the letter you would put in here is t. Or in the calculator, you can just punch an x, that's fine. And then say if you wanted it evaluated at, say, 10, you would put 10. So in this case, pi divided by 2, I actually input pi over 2. So again, I have brackets to make sure that I'm not losing anything. Hit equals over here, and it gives me the value of negative 4.629. Here you could truncate it, so either or negative 4.629, or you could do negative 4.630. So round up brings it to 0.30. All right, same idea. I'm showing one more here, n derive. So again, I click that math button, punch the number 8. It'll automatically take me back to the screen with this piece filled in. I type in ln of x with respect to x, and then 205 equals 0.00487. So here I could do 0.004 or 0.005, depending on if I truncate or I round. Alrighty, so the last question here was talking about question 18, where the sentence version of it was a little bit confusing, especially with the solutions. So I have the solutions here, and I'm going to try to break these apart into what is happening. So question 18 says the number of championships Sully has won while coaching basketball. So C is some value. T is the number of years since 2002 for the function C of t. And then it tells us at C of 12, so 12 years since 2002, so this 12 here refers to 12 years after 2002. So I'm going to just quickly do 2002 plus 12, so I get 2014. So this is how they get that 2014, and then the value 3 represents 3 championships. So if we think about the graph C of t for a second, I'm just going to show us the positive side, but basically 0 for t is over here, 12 is over here. Really, this is 2002, this is 2014. They just didn't want to use big numbers. And then we have 3, 2, 1. So maybe this is a graph that represents some sort of predictive function for how Sully has been doing. So it doesn't make sense for it to be going down, but maybe it's not really a straight line. So maybe it's something like this. The important thing for us, important thing for us though is that this value is given. We don't really know what's happening everywhere else. We don't really care, but we know at this point we are at 3 championships for Sully. Now, C prime of t, remember this is the slope, or this gives us the equation for the slope of the tangent line. So if I have something like C prime of 12 is equal to 0.4, then this is the slope at the point t equals 12. So basically I am making a tangent line right here, and in this case, let me zoom in, and it's a little bit above here. So what's important for us is that the slope is equal to 0.4, and it's positive 0.4. So that means that Sully is on average increasing the number of championships that he wins. So this is why they use the word increasing, is because it's a positive slope. Now we have to take a look at the units. We have championships as our y, and we have time per year. So at 2000 or in 2014, the rate at which, oops, spelling Friday, is, well, if we're sticking with units, 0.4, championships per year. Because remember, our units are y over x. So on average, he's winning at 0.4 championships per year. So we would expect the next win to occur sometime between 2 to 3 years in the future. Sort of the better you are, the steeper this line is going to be, because you're going to win more often. The less good you are, this line is going to be shallower. So, for example, he was doing really good here, and then less good here. It might make a little bit more sense with the second example here, so I'll post that. So D is the distance in miles from home when you walk to school. H is the number of hours since 7 a.m. for the function d of h. So if I look at the function d of h, I have two things. I have the distance in miles, so I'll have 0.5, or I'll do 0.25, why not? 0.5, 0.75, and then I have 1. Now remember, we don't really care about these, but we'll use them here anyways. And then the bottom is time. Now, the units are in hours, and this is hours since 7 a.m. So the first thing is 0.2 hours is, well, 0.2 times 60, which is going to give me 12, so it's 12 minutes. So first part of the answer, this is how they get that 712. So evaluating the function, it says at 12 or 712, you're half a mile from home. So you're somewhere here. Then it says d prime of this point is equal to negative 11. So here, remember, this represents the slope of the tangent line. So you're moving in the negative direction with a slope of minus 11. So I'll say m equals minus 11. Well, if this is the distance from home, then once you get to 0, you're at home. So if we were to think about what's maybe happening, maybe you leave at 7, you hop on a bus or get in a car, and then, whoops, you forget something, so you turn around and you head back and you get home, and then you get out of your car and you walk. So your graph looks something like this. Again, we don't really care what the graph looks like, because all we're concerned with is what's happening here. But this is the second point, is that here your slope represents your rate of change. So the second part is at 712, exactly, you are going home at, well, again, 11 is your rate, and then it's going to be miles per hour. And how I get that is, again, we have our x over y for our units. Or sorry, y over x, my bad. So a couple things to take away. When we talk about our derivative, we're referring to the slope at a given point. So think about the units that are happening. In this case, we were looking at championships and years. So your rate is going to be how many championships per year you're winning. It's going to give you a weird number like 0.4, that's fine. You're winning at the rate at that specific time. And it actually doesn't matter what the graph is doing anywhere else. And this is sort of the power of calculus, is that your graph doesn't have to be a straight line to figure out how fast you're going at any one time. Your graph, if you're actually driving a car, is going to be all over the place because you're going to be stopping. So your graph is going to probably look more like this, and then you're going to you're going to come home, hit a couple traffic lights. So we want to be able to tell how fast you're going at any exact time, but without doing a graph, try to think about what is sort of happening behind the scenes. So the main part here is that your derivative here is sort of it is a rate of change. The important things is what time or what point is it happening at. So you need to include this 7:12 a.m. So what time or what year. So here it was in 2014. And in your regular function case, that's referring to what the number is. You're half a mile from home, you've won this many championships, you are whatever that y value is. For the derivative, it is how fast that y value is changing. So hopefully this helps clear up some things. If you have any other questions or if any parts of this were unclear, feel free to ask and I can add some stuff. In case that's all I have for you today. The one last thing I'll mention is that this is available on our OneNote. So if you go to our classroom notebook, you can find this and take pictures of it, or you can take screenshots of the video. But in any case, that's all I have for you today. Take care, stay safe, have a good one.